Dear students, in the last class we discussed interference at an air wedge. In this method, the two current sources are derived by the method called division of amplitude. And one more method of deriving current sources by division of amplitude is by using the Newton's ring setup. In the Newton's ring setup, there is a plain glass plate over which a plano-convex lens is placed. A plano-convex lens. So this is a plano-convex lens placed over a glass plate. So this is a setup actually we use in the laboratory to observe the fringe pattern in Newton's ring setup. Here the fringes are circular in shape. That's why they are called as, the fringes are called the rings. That's why this setup is called Newton's ring setup. This is a setup we use in the lab to get the Newton's rings. So here the current source is derived by division of amplitude. Here we have a plain glass plate. On that a plano-convex lens is placed. Plano-convex lens of very long focal length is placed. So that at this point the glass plate and the lens, they are in contact, and as you move on either side towards the end, the thickness of the air film, see here there is a gap between this plano-convex lens and the glass plate. A small gap is introduced between the plano-convex lens and the glass plate. In that gap is filled with air. The small gap is filled with air. At this point, lens and the plate are in contact, and as you move on either side, the thickness of the air film goes on increasing. Here we have the air film. Here also there is air film. Its thickness goes on increasing as you move towards the end from this point of contact. Why? See here, the light is incident. See, this is the incident ray. A monochromatic light is incident normally on the setup. It falls normally on the setup, and this incident ray, see at this point, this is the upper surface of the air film. At this point, that incident ray gets partially reflected and partially transmitted. This transmitted ray again falls on this surface, the lower surface of the air film inside this lens and the plate. At this point again there is reflection and refraction. The refracted ray moves this way, the reflected ray moves in this direction. So that these two rays, these two are derived from the same incident beam. So that these two behave like the coherent rays. These two reflected rays behave like the coherent rays. They interfere to give the fringe pattern, and the fringe pattern consists of alternate bright and dark rings. So the fringes are called Newton's rings. And here at this point, lens and the plate are in contact, so that at that point always in reflected light, in the fringe pattern, always at the center a dark spot is observed. In reflected light, in this setup, at the center always a dark spot is observed, and on surrounding that dark spot, that central dark spot, there are alternate bright and dark rings of increasing radius or increasing diameter. And as the order of the ring increases, the rings, they will come closer and closer. The gap between any two successive rings goes on decreasing as the order increases. Order means the number of rings or the fringes from the point of contact. So this is how Newton's rings are produced in reflected light. Now to find the expression for radius of the Newton's rings, to get the expression for radius of Newton's rings in this reflected light. So here let us consider the lens, the plano-convex lens of long focal length. Let R, capital R, let R be the radius of curvature of this plano-convex lens, and let A be the center of curvature of this plano-convex lens. See here, A is the center, and then this surface, this part of the lens forms the part of a circle, and if you complete this arc, this is the arc, this makes the arc of a circle. curved portion of the convex lens, which is the part of a circle. So if you complete that circle, if you complete a circle like this, you get a circle like this with this curvature of the lens, a part of it. So that we get a circle with center A, center of curvature, then AG is equal to AO. AG is equal to AO, nothing but the radius of curvature of this plane of convex lens. So that OG is the diameter, OG is equal to 2R. Now, here O is the point of contact. Here we have the air film between the lens, plane of convex lens and the glass plate. Here, let us consider a chord DC. Draw a chord DBC. Anywhere in this region of air film, inside the lens and the glass plate. Draw a chord. Now, here from the diagram see, OA, AGs are nothing but radius of this plane of convex lens. BG, from the diagram, BG is nothing but OG minus OB. This BG is equal to OG minus OB. And OG is nothing but twice the radius, diameter twice the radius 2R, and OB, this OB is nothing but thickness of the air film. This OB is equal to this much. Let T be the thickness of the air film at any point inside this lens and the glass plate. So here I have taken the chord at this point, not exactly at the extreme. I have taken the chord here corresponding to this chord drawn. The maximum thickness is taken as T. So that our BG becomes 2R minus T. Here OB is nothing but thickness of the air film corresponding to this chord. Now using these things, let us get the expression for radius of Newton's rings, bright as well as dark. See, in the field of view there are alternate bright and dark rings are observed. And one more thing here, see why the fringes are circular in shape. Why the fringes are the rings in this Newton setup? The reason is, see here, at this point lens and the plate are in contact. So thickness of the air film 0. And as you move on either side, thickness of the air film increases gradually on either side. See, if you consider these 2 points, thickness same. These 2 points again thickness same. These 2 points thickness of the air film same. Here extreme thickness are equal. This way the thickness of the air film increases gradually on either side. That's why the fringes are circular in shape. The locus of all those points which are having the same thickness of air film are nothing but, or is the locus of the points having the same thickness. It's nothing but a circle. That's why the fringes are circular in shape. This is the reason. Now, to get the expression for the rings, either bright or dark, let us consider from the geometry. Now, consider this diagram from the geometry. Here, dB into BC. dB into BC. This is the chord we considered. dB into BC is equal to OB into BG. OB into BG. This is from the geometry. dB into BC is equal to OB into BG. And here dB in nothing, dB equal to BC. dB is equal to BC. It is nothing but this is a point where a certain fringe is formed. Up to here. See, let us consider the mth fringe at this point. Consider the mth fringe at this point. Let Rm, R suffix m be, Rm be the radius of that mth ring, either bright or dark. Consider the mth ring produced at this point. Produced corresponding to this thickness T. Mth ring, either bright or dark, produced corresponding to the thickness T. So that the rings comes like this. So that this distance, nothing but radius of that mth ring, let it be Rm, small letter R, Rm. So that dB into BC, both are same, equal, nothing but Rm into Rm is equal to OB. OB is thickness into BG. What is BG? BG is 2R minus T. So that if you simplify this, you get R square m equal to 2RT minus T square. The thickness T, the thickness of the air film is very, very small. Such a thin air film is introduced so that T very small, T square still small, it can be neglected. So that we get R square equal to 2RT. This gives radius of the mth ring, see either dark or bright in general, radius of the mth ring is square root of 2RT. Thus, radius of the ring produced there, Newton's rings produced, depends on radius of curvature of the cranioconvex lens as well as thickness of the air film at that point where that particular ring is formed. Now, let us find out the radius of the dark ring. Let us consider mth dark ring in reflected light. Mth dark ring in reflected light, we had derived the general expression, the condition to produce dark ring, dark fringe in reflected light is 2nt cos r equal to m lambda. This one we had derived in the previous class. 2nt cos r equal to m lambda, general condition to produce a dark ring, mth dark ring. M takes the values 1, 2, 3 and 0, 1, 2, 3 and so on. See here, the angle of reflection is very, very small, so that cos r becomes 1, then this equation becomes 2nt equal to m lambda, or from this, the thickness of the film corresponding to that mth dark ring is m lambda by 2n. This is T. Substitute this T in this expression. See, this is the expression for the radius of the mth ring. Here we have considered the mth dark ring. Therefore, the radius of the mth dark ring becomes 2r into m lambda by 2n or m lambda r by n. So, if the medium introduced between the lens and the glass plate is having refractive index say n, in that case, the radius of that mth dark ring becomes m lambda r by n. M lambda r by n. N is refractive index of the material of the medium between the lens and the glass plate. But here in this case, the introduced medium is air, and for air n is 1, so that radius of the mth dark ring becomes square root of m lambda r. This is the general expression for radius of mth dark fringe produced in air in Newton's ring setup. The medium is air. And m takes the values here 1, 2, 3 and so on. Order of m, order of the dark fringe is taken as dark ring or fringe taken as 1, 2, 3 and so on, because 0 is not considered, because in this system, in this pattern, in reflected light, Newton's rings in reflected light, the center is always dark, a spot is observed, it is not considered as a ring. So m value is not 0. For m0 we get the center, it's not a ring. That's why order is 1, 2, 3 and so on. This is the radius of the mth dark ring in Newton's ring setup. Now consider the bright fringe. Suppose at this point where the thickness is T, at this point mth bright fringe is produced. Mth bright fringe. Let Rm be radius of that mth bright fringe. And in general, the condition to produce bright fringe in reflected light. Bright fringe in reflected light is 2nt cos r is 2m plus 1 lambda by 2. The bright fringe in reflected light produced when this condition is satisfied, and again cos r becomes 1, r small cos r becomes 1, so that 2nt is equal to this one. From this we get T as the thickness corresponding to that mth bright ring as 2m plus 1 lambda by 2 by 2n. Or if you substitute this T in the general expression for Rm, Rm is this. If you substitute T, you get Rm as this. Rm corresponding to the bright. Radius of the bright, mth bright ring. Radius of mth bright ring is given by the square root of R into 2m plus 1 lambda by 2n. This is for any medium. If the medium is air, when the air film is introduced between the lens and the glass plate, n becomes 1. So that radius of mth bright fringe becomes square root of r into 2m plus 1 lambda by 2 with the order 0, 1, 2, 3 and so on. Here order is taken as 0, 1, 2, 3 and so on. And this is about the radius of Newton's rings, either bright or dark ring. For a bright dark ring, radius is given by root m lambda r in air, or it is root m lambda r by n in any other medium having refractive index n. For a bright ring, radius is root of r 2m plus 1 lambda by 2n for any medium. For air, it is square root of r into 2m plus 1 lambda by 2.